Hi everyone, welcome to my channel Civil Maverick. In this video, I'll solve first 130 questions of standard material from the iconic book GUPTA and GUPTA. I hope this problem solving video will be immensely beneficial to you for your any upcoming engineering related comments or examination. Thank you. So let's solve the first question. The question is modulus of rigidity is defined as a ratio of. Now what is modulus of rigidity? Suppose this is a block we have. Right now, suppose this is surface, this is B and this is L. I have applied a load P. This surface will have what? This surface will have what? Shearing stress. Now what is shearing stress? Shear stress is equal to P by P into L. Now what will happen? This surface will try to slice down with respect to this bottom surface. In that case, what we'll have? We'll have shear strain. Suppose this is Y. You can draw again here. This is Y. This is trying to slice down. So this is delta X, delta X. So this is Y. Okay. And this shear strain is equal to what? Del X by del Y. So del X by Y only. Then what is G? G is what? Modulus of rigidity. Is what? Shear stress by shear strain. Right? So what is the answer? Answer is B. This longitudinal stress to longitudinal strain is called what? Young's modulus or E. And the stress, direct stress to volumetric strain is called what? Bulk modulus is equal to what? K. Always remember that, right? Next question is, if the Young's modulus of elasticity of a material is twice its modulus of rigidity, then the Poisson's ratio of the material is. Now, there are some standard formulas you have to remember. The first one is E equal to 2G1 plus mu, E is equal to 3K 1 minus 2 mu, E equal to 9kg 3k plus g, then mu equal to 6k minus 2g 3k plus 2g, right? These are the four standard formulas you have to always remember, right? Now what is the value of, now what are they asking? They have given the Young's modulus E, then the G value is given modulus of rigidity, then you have to find the mu. We solve this question through this formula, we get the value of mu equal to 0. So this is the correct answer. Next question is the limit of proportionality depends upon limit of proportionality. Now what is limit of proportionality? See here, if this is what? Mild steel. This is mild steel, okay? Mild steel. This is what? Strain, and this direction stress. This point is called, this is proportional limit, this is elastic limit, this is upper real limit, and this is what? Lower yield limit. Now, this type of curve we see only in case of mild steel. Now, if I use the HYSD bar concrete, we don't get this type of curve. We get something like this, right? So here, this straight line, right? Straight line, right? This point is called proportional limit. Hooke's law is valid only up to the proportional limit, right? Stress to strain is constant in case of up to the proportional limit. That is why Hooke's law is valid. So this typical graph is shown only in case of mild steel, right? That means what? Limit of proportionality depends only upon the area of cross section. No, it is not correct. Type of loading, no. Type of the material, yes. Mild steel has got a defined yield stress value. HYSD bar has got different yield stress value, right? So it is a property, material property that is giving to this type of curve. The correct answer is what? Type of material, C. Next question is, for an isotropic homogeneous and elastic material, obeying Hooke's law, the number of independent elastic constant, right? Now, see here, there are four formulas. This, right? Now, if you can find two values, either G or E, you can find a third one mu. Here also you can find, if you find a K value, G value, you can find a E, right? That is what, if you can have the value of two independent elastic constant, then you can easily find a third constant. So the number of independent elastic constant is what? 2 in case of isotropic homogeneous material. Now let us take the point number question of 6. If all the dimensions of a prismatic bar are double, then the maximum stress produced in it under its own weight. Now let us see. This is a prismatic bar. This is hang on this fixed support, right? Now this is prismatic bar because the cross section BD is same throughout the length. Now what is the stress under its own weight? Stress or force by area. Now force is what? It's unit weight into volume, because we have to find the force due to its own weight. And the gamma is what? It's unit weight. Gamma is what? Unit weight. Now gamma is volume is what? A into L by A into gamma L. That is what? The stress is the function of only the length, right? If you increase the length to 2 times, what will happen? The stress will also become 2 times. The answer is C. Now question number 7. This is the standard formula to remember. E is equal to what? 3K 1 minus 2 mu. Okay. Question number 8. The limiting values of Poisson's ratio. You have to remember -1 to 0.5. Just remember. Question number 9. The elongation of the conical bar under its own weight is equal to. Okay, this is a prismatic bar. Now what is the elongation here? Elongation of prismatic is what? 2e. Now if I take a conical bar, this length is L. Elongation is equal to what? 6e. That is what? Prismatic bar has 3 times more elongation than the conical bar. So answer will what? This 1/3 of a prismatic bar of the same length. 9. 9 answer is C. Now question number 10. If a material has identical properties in all directions, it is said to be. Now what is isotopic material? What is homogeneous material? Let me take an element. This direction is X, this direction is Z, and this direction is Y. Let me take 2 points A and B. Okay. Now first, what is homogeneous? What is homogeneous? If the mechanical properties at A, along the x direction is same with the mechanical properties at B along the x direction, and also if the mechanical properties along y direction at A is equal to the mechanical properties along y direction at B, similarly other directions, so Z or in any other directions are same, then the material is said to be what? Homogeneous. That means in homogeneous what will happen? Mechanical properties are same toward the length, right? For the length. That means if I take the stress value, is sigma A along x direction is sigma B along x. Similarly, sigma A along y is equal to sigma B along y. Sigma A along z equal to sigma B along z. If you take any other direction also, suppose this is x, this is y, this is z. You can take x dash, y dash, z dash, x1, y1, z1, any direction you can take. If you find all the properties along the particular length same, then it is said to be what? Homogeneous. Now, what is isotropic? Mechanical properties. Same in particular point along all the directions. So if I take the point A, suppose I take any direction, 1 directions, 2, 3, 4, 5, 6, 7, 8. So if I take the stress, sigma 1, sigma A at 1 is equal to sigma A at 2 is equal to sigma A at 3 equal to sigma A at 4 is equal to sigma A at 5 is equal to sigma A at 6 equal to sigma A at 7 equal to sigma A at 8. And this is called what? Isotropic. In a particular point, if the mechanical properties are same along all the directions, it is called isotropic. Now, what is anisotropic? This is the opposite of isotropic. Iso means what? Same. The meaning of iso means what? Same. So if I take anisotropic, it is ulta. That means what? Sigma A1 is not equal to sigma A2, is not equal to sigma A3, is not equal to sigma A4, is not equal to sigma A5, is not equal to sigma A6, not equal to sigma A7. This is called what? Anisotropic, right? Anisotropic. Now, what is homogeneous? Sorry, now what is then orthotropic? Orthotropic. If the mechanical properties are same along 3 perpendicular directions in a particular point, that means if I take sigma 1 and sigma 3 equal to in one particular direction, you can take that can be like if I take, suppose I take sigma x, sigma y, sigma z along 3 mutual perpendicular directions. If the mechanical properties are same, this is called what? Orthotropic. Orthotropic. Now, suppose I take sigma x dash 1, then it will be sigma y dash, sigma z dash. These x, y, z are what? 3 mutually perpendicular directions. X dash, y dash, z dash are what? 3 mutually perpendicular directions. If the properties are same along 3 mutually perpendicular directions, this is called what? Orthotropic. Orthotropic. The perfect example of orthotropic is what? Wood. Perfect example of isotropic and homogeneous is what? Isotropic plus homogeneous is what? Steel. A perfect example of isotropic and homogeneous. Now let's see the question now. If a material has identical properties in all directions, it is said to be. Now in this question, it is saying that identical properties in all directions in a particular point. Although it is not hidden, but it is saying that in a particular point. So answer is what? Isotropic. Isotropic. Homogeneous will be what? Along a particular length. If the material property is same along the particular length, x direction length, y direction length, z direction length, right? Then it is said to be what? Homogeneous. Okay. And steel is what? Both steel is what? Both isotropic and homogeneous. Wood is what? Orthotropic. Right? So you have to remember this. Now, okay. The next question is, 2 bars of different materials are of the same size and subjected to the same tensile forces. If the bars have unique elongation, the ratio of forces 7, then the ratio modulus of elasticity of the 2 materials. Now, what is the elongation formula? Suppose I take one. Same, see the question. same tensile force, right? The materials are different. That means E is different. That means P, same size. Size means what? Same length, obviously. P L1 A. Sorry, this is not L1. P L by A E1 is equal to P L by A E2. Sorry, this is equal to delta 2. So delta 1 is PL by A1, delta 2 is what? The second material PL by A2. So if you divide del 1 by del 2, you divide del 2, that means what? You get 4 by 7 is equal to E2 by E1, or E1 by is equal to 7 by 4. Answer is A. Now let's see the question number 12. So one prismatic bar is there. L, B, and depth is P. P tensile force is applied. Now, what is the final volume? Now, what will happen? Due to the tensile force, the length will increase, and due to the Poisson's effect, the rate and the depth will decrease. Now, what will happen in the final length? The final length is what? L plus del L. Because the length will increase, and the final breadth is what? B minus del B. Final depth, the D minus del D. So what is the final volume? The final volume is what? L plus del L, B minus del B, D minus del D. So let me take LBD common. So what will happen? 1 plus del L by L, 1 minus del B by D, 1 minus del D by D. Right. Now LBD is what? Initial volume. Let me take as V. Okay. LBD is what? Initial volume as V. So V into 1 plus del L by del is what? Epsilon X, 1 minus epsilon Y minus epsilon Z. Let me take the epsilon X as P only, and this Y and Z will be same, right? Epsilon Y and Z will be same only. So this is 1 minus mu into E, 1 minus mu into E. So this is equal to 1 plus E, 1 minus mu E whole square. The answer is C, right? Now this question is, a composite bar of steel and copper is heated. The copper bar will be under what? Obviously tension Y. About this is okay. Suppose this is one is copper, the one is steel, composite bar, okay? Or let me not draw like this. Let me okay, suppose this is we support. One is copper, this is copper, and this is what? Steel. Now, the coefficient of thermal expansion of copper is more than steel, right? But as this is a composite material and this is under a fixed support, the total length cannot increase, right? Total length cannot increase. Total length has to be what? Same. Isn't it? The total length has to be what? Same. So what will happen? As this alpha C is more than alpha S, what will happen? The copper will try to expand more. compared to steel, right? But the total length has to be same. To keep the length same, what will happen? This will come under compression and steel will come under what? Tension. Only in that case the total length will be same. So what will happen? The copper bar will be under compression. That will be right. Now this is for steel, okay? This is not required, this part. So let us directly move to okay, this and principal stress question 27, right? Question 27, right? At a point in the strain body current to unequal unlike principal stresses P1 P2. The maximum stress is given by, see, maximum stress formula always have to remember. Maximum stress is equal to radius of the Mohr circle or or Q or difference of principal stress by 2. Any one of this. Okay? Any one of this. So what will happen? Here, two unequal principal stresses P1 P2. That means sigma x equal to P1 here only. And sigma y2 is equal to what? P2. Unequal, unlike. Unlike means what? If one is tension or other one is compression. Like means both will be tension or both will be compression. Unlike means the nature is different, right? So what the radius r? Now r is what? P1 minus P2 by 2 whole square. There is no shear stress, right? Equal to P1 minus P2 by 2, right? This is similar difference of the principal stress by 2. Answer is, now the answer will be what? P1 minus, you can write here minus P2 into P1 plus P2 by 2. Condition D. Why? Because I have written minus, because one is tension, the other one is compressive, right? That is why I have given minus, right? Now the next question is, if a point in a strain material is subjected to equal normal and tangential stresses, then the angle of obliquity is. Now what is angle of obliquity? Suppose this is what the plane of tau max, and this is normal stress, and this is the resultant stress. This is phi. This phi is what? Angle of oblique. Now this tau max is equal to, and this should become what? Obviously 45 degree. Now the next question is, the plane of measure the plane of maximum obliquity is inclined to the measure principal plane at an angle. Now see here, suppose okay, this is suppose P1, P2. This P1 is what? Measure principal. Yes. Okay. Now what are they asking? Suppose okay, I take a plane here. Okay, this is theta 1. Now here will be one normal stress, one resultant R1, and here one tau 1. This is what? Now you have to find this theta in terms of this phi 1, where phi 1 becomes the maximum value. So suppose this is not a maximum value. Suppose we have a different plane that it inclined at theta 2. Theta 2. So here what we will have? This is tau 2. Here this is normal 2. Then we have the resultant R2. Then this we have the phi 2. So we have to find that phi 1, phi 2, phi 2. That phi where phi becomes maximum. And after we reach a maximum value, we have to find the theta value in terms of this maximum phi value. And that maximum, that theta gives what value? Theta is what? Pi by 4 plus pi max by 2. So this can be drawn through Mohr's circle. Okay. We have to find that theta, that plane where the angle is theta, and this theta has to be expressed in terms of the phi max value, right? This is equal to pi by 4 plus pi max by 2. This is drawn with the help of Mohr's circle, right? Now the next question. Okay. Now the next question is, a point in a strained body is subjected to a tensile stresses of 100 MPa on one plane and a tensile stress of 50 MPa on a plane at right angle to it. If these planes are carrying a shear stress of 50 MPa, then the principal stresses are inclined to the larger normal stress at an angle. Okay, let me draw it now. Suppose here 100, 150, right? And what is the shear stress? 50, 50. Now you have to find the angle. Okay, you have to find the angle for which the principal stresses are acting, and what is the inclination of that plane with the measured principal plane. So that means this theta p. Theta p is what? Angle of principal plane with the measured with the not measured, with the larger normal stress or the normal stress, right? So you have to remember the formula. Tan 2 theta p equal to 2 tau x y one so into 50 by 100 minus 3. Mhm. This answer. Right. This we have to solve. Now let us look at question number 32. Okay. If a prismatic member with area of cross section A is subjected to a tensile load of P, then the maximum shear stress and its inclination with the direction of load respectively are. Okay, see here. This is a prismatic member. Okay, here P is applied P by A, right? Now, obviously, the shear stress is always the maximum shear stress is always inclined at 45 degree. And what is the value of the maximum shear stress? Tau max P1 minus P2 by 2. Here P2 is 0. What is P1 now? P by A by 2. So P by Y. Answer is B. Question number 33. The sum of normal stress. Now see, this is sigma x, this is sigma y. Let's take a plane. This is sigma x dash and this is sigma y dash. Now this sigma x plus sigma y is always equal to sigma x dash plus sigma y dash equal to constant. Answer is A. Next question is the radius of Mohr circle for two equal unlike principal stresses of magnitude P. Now what is the formula of radius of Mohr circle? R equal to sigma x minus sigma y by 2 whole square plus tau xy square. So two equal unlike, that means what? Suppose P1 equal, right? Minus P2 minus P1 by 2 principal stress. Tau is 0. It gives what? This is whole square. So P1 square equal to P1 equal to, that means answer is what? A. Shear stress on principal planes is 0, right? All of you know that. On a principal plane, there is no shear stress, right? Now let us look at the question number 36. The state of pure shear is produced by. Now what is pure shear? That means in pure shear, the shear stress has to be 0. Suppose this is sigma x, this is sigma y. And suppose we want to produce pure shear on this plane. Tau xy, tau xy. On this particular plane, tau dash xy, we want to produce pure shear. So that means what? The normal, this has to be 0, right? That means tau, the sigma x dash is 0. Now what is the formula for sigma x dash? Sigma x plus sigma y by 2 plus sigma x minus sigma y by 2 cos twice theta plus tau xy sine twice theta. Okay. Now if we want to make this term 0, let us make all the term individually 0. So to make this term 0, this term, what we have to do? This tau x has to be 0. If tau xy is 0, then this becomes what? Principal stress, right? Sigma y becomes the principal stress, right? Tau xy is equal to 0, right? So now, if this theta is 45 degree, cos 45 cos 90 equal to 0. So this also becomes 0, right? So theta equal to what? 45 degree. So then this sigma x plus sigma y by 2, that means if then sigma x become P1, so P1 plus P2 by 2 equal to 0. That means P1 is equal to minus P2. That means we have to apply two principal stress of opposite nature. If P1 is P1 is tensile, then this P2 has to be what? Compression. Right. So the answer will be what? This A, tension in one direction and equal compression in particular direction. Right. This is the answer. Next question is 37. Question number 37. A prismatic bar is carrying only an axial force, two planes on which normal and shear stress are equal are inclined to the axial force at angles. Okay. First let me remove this. Okay. Let me draw the prismatic bar. So this is a prismatic bar. This is carrying only tensile, only axial force. It can be compressive or it can be tensile. Right. The two planes on which normal and shearing stress are equal. Okay. The two planes on which normal and shearing stress are equal. Right. Let me draw one particular point. Suppose I take a point 1, and I enlarge it. Okay. Enlarge the point 1. So here, suppose my x. Okay, only sigma x is carrying, right? Now there will be stress. This is point number 1. Okay, there will be stress. This theta and tau. Now what are they saying? This tau xy s is equal to sigma x. What is the tau x formula? Minus sigma x minus sigma y by 2 sine twice theta is plus tau xy cos twice theta is equal to sigma x plus sigma y by 2 plus sigma x minus sigma y by 2 cos twice theta plus tau xy sine plus theta. Now, look at the question. Carrying only an axial force. That means what? This sigma x becomes the principal, right? Because there is no shear and there is no what? There is no shear and there is no stress perpendicular to this direction, right? Tell me only P1 is carrying. That means this becomes 0. This becomes 0. Tau xy is 0. Tau xy is not present here. So sigma, that means 0. If sigma x P1 and sigma y is 0, tau xy equal to 0. So sigma 2 sine plus theta is equal to cos theta. Okay. Now if you solve this, P1 cos minus sine twice theta is equal to 1 plus cos twice theta. So sine twice theta plus cos twice theta is equal to 1. Is equal to minus 1. Okay, minus 1. And if you look at this equation, only option B satisfies this. Only option B satisfies. If you put the value of, if you put all the value of from the options, okay, then you'll find that only option B, this satisfies this equation, right? So answer will be what? B. That is the way you have to solve the question. Sine twice theta plus cos twice theta equal to minus 1 and If you put all the values from here, this value, this on this equation, and you find that only option B satisfies the equation. So under answer will be what? D. Right. Next question is according to Rankine's hypothesis, the criterion of failure of a brittle material. See, there are some theories of failure. This maximum principal stress is for Rankine, and this is for brittle material. Always have to remember brittle material, right? Maximum shear stress. This is for ductile, right? This is for ductile. This you have to remember. If maximum principal stress is concerned, this is only for brittle material. Why brittle material? Because brittle material fails in tension. Brittle material fails in tension, right? It cannot sustain a tensile load. That is why the theories of failure for brittle material is calculated using the principal stress values. And this theory is given by Rankine, right? Rankine. Okay, so this is the answer. Next question is the maximum bending moment in a beam occurs where the deflection is zero, shear force is maximum, shear force changes sign. Obviously, this is the answer. Shear force changes sign. If I look, but there is a point that I would like to mention here. Now, what is the bending moment diagram? BMD, right? I'm going to just CFD, SFD, sorry. This is the SFD. SFD. Now, bending moment is changing sign at this location C. C, right? Here, when the bending moment is changing sign, when the shear force is changing sign, the bending moment becomes what? Maximum, right? So, this is the answer. But this is applicable only in case of what? Simply supported beam. This is not this answer is not applicable for fixed beam, because if you look at the fixed beam, let me show you a fixed beam. Let me show a fixed beam here. What there? P load is there. P. Okay. L by 2, A, P. The fixed end moment is what? Minus PL by 8. This you have to remember always. PL by 8. Okay. And reaction RA, P by 2, RB is equal to P by 2. Right. Now, if I draw the max bending moment diagram, this is for fixed BMD. Must PL by 8, right? And this is PBMD. What is the value here? P by 2 into L by 2 equal to PL by 4. Now, if you do superposition of these two, what will happen? Right. This is minus PL by 8. This is minus PL by 8 minus. And this okay. Only this is what is remaining, and this is remaining, right? And this value is how much? This value is how much? PL by 8. This value is PL by 4 minus PL by 8 is equal to how much? PL by 4, right? Oh, sorry, PL by 8. This value is how much? This value PL by 8. This portion is cancelled out. Now look at the shear force diagram. This is what? This is BMD. Now look at the shear force diagram. Look at the shear force diagram. Shear force diagram changing sign. Right? This is the shear force diagram. FD, BMD. So this is the final BMD. Yeah? Final BMD. This is 3 BMD. Now this is the answer, right? Now we see here now see here the shear force is changing sign here. But when the shear force changes sign, what is the value of maximum bending moment? Here is PL by 8, so here is also PL by 8. So this is not applicable for fixed beam. This is applicable for only what? Simply supported beam. Where it is when this shear force changes sign, bending moment becomes maximum. Right? This is only applicable for what? Simply supported beam, not for fixed beam. Remember that, not for fixed beam. Right? Okay. Now let us find the solution of question 40. A simply supported beam of span L carries over its full span a load varying linearly from 0 at either end to the W per unit length at the midspan, the maximum bending moment. So if I draw a beam, so this is the beam, right? This is L by 2, A, B, C, and this is how much? This value, W per meter, right? Now let us find a reaction. RA is equal to RB, obviously, is equal to half into L into W by 2, WL by 4. Now bending moment at T equal to maximum bending moment is equal to RA into L by 2 minus half into L by 2 into W, right? See, because this is here, this triangle has load of what? Half into L by 2 into W into, now this triangle will have a CG at this particular point here, right? This is the point. So this is how much? This is L by 2 by 3 from C, right? Into L by 2 by 3 equal to WL by 4 into L by 2 minus 4, 8, 24 WL square by 24, right? So if I take 24 common, 8 WL square minus WL square equal to WL square by 12. So this is the answer, 40B. Right. Midspan, not quarter, so midspan is equal to WL square 12. Right. Now let us look at the question number 41. The rate of change of bending moment. Okay, see here, dm by dx is equal to shear force S and ds by dx equal to loading. That means bending moment is greater than shear force in terms of degree. That means bending moment is 1 degree higher than shear force is 1 degree higher than loading, right? We can understand this with the help of this UDL. Suppose this is a UDL. A, B, C. Now what is the bending moment diagram? BMD. What is the shear force diagram? This is the shear force diagram, right? Now see, this is the equation of what? Parabola, right? Equation of parabola, right? Now this is what? Uh, the loading, the bending moment equation is what? The bending moment equation is what? Ra into x minus omega s square by 2. And here, what is the equation of shear force? Ra minus w into x, right? Now you can see here clearly, this is what? 2, right? 2 degrees there, and here what? What is the degree at 1? That means this is 2 degree, this is 1 degree, right? And what is the loading? Load is in W only, right? W only, right? That means what? This bending moment is 2 degree, this is 1 degree, this is 0 degree. So bending moment, if you differentiate the bending moment, what you will find? You will find a shear force. If you differentiate the shear force, you find a loading, right? So what is the answer? Answer is A, shear force, right? Next question is the diagram showing the variation of axial load along the span. Axial load, okay, not the transverse load. So this will be a truss diagram, okay? Axial load, because you are applying, like, this is the axial load, right? And this direction. So this is what? Thrust. Now let us solve the question 43. The difference in origin of the shear curve between any two sections is called. Now I told you that rate of change of moment is equal to shear force, and rate of change of shear force equal to what? Loading. Okay. Now to solve this question, we'll take the help of a numerical. So let us solve this with the help of numerical. Suppose this is an UDL. Here I have taken 2 points A and B, and here the load is 10 kilonewton per meter. And suppose the length of the beam is 10 meter, and one concentrated load is acting 100 kilonewton at C. This C is how much? At 4 meter from A. Obviously this is 6 meter. And we take 2 points D and E. This D is how much? At 2 meter from C, and this is also 2 meter from C. So we'll find the difference of shear force between C and E and D. Then we'll try to solve it. So to calculate this, we have to first find the reactions, right? So bending moment at B equal to 0. At B equal to 0. So Ra into 10 minus 10 into 5, 10 into 10 into 5 minus 100 into 6 equal to 0. Solving, we get Ra equal to how much? 110. Now we have to find the shear force at D, C and E. Okay. The shear force at D is how much? 100. Ra minus 10 into, this is 2 only, right? This will be 2 into 2 equal to 90. Shear force at E, Ra minus, okay, I'll find the shear force C. First, I'll find the shear force at C. Shear force just left of C is how much? Ra minus 10 into 4 equal to 70. Shear force just right of C, Ra minus 10 into 4 minus 100, because now right side this the 100 kilo load will also act, and this becomes I think 110 minus 40 minus 100 to minus 30, right? That's shear force at E, how much? Ra into 10 into 6 minus 100 plus minus 50, right? Now we'll draw a shear force diagram. Let me draw a shear force diagram. Draw the beam again. Right. The shear force diagram will be something like this. This is how much? RA 110 and D how much? 90. So 90. Just left of C. How much just left of C is what? Just left of C is 70. Just left of C is 70. This is straight line only. Just right of C was minus 30. Minus 30. Just at E is how much? Minus 50. So this is 110. This is 90. This is 70. This is minus 30. And this is how much? Minus 50. Okay. This is the shear force diagram. Obviously, this is 70 plus 30 has to be 100, right? This load is acting. Now see, now this is the point D and this is the point E, right? Now what I said, rate of change of shear force is equal to the loading. Now what is shear force difference between D and E? Shear force at D minus shear force at E. How much? 90 minus 50 is equal to 140. Okay, isn't it? Now what is the loading? This UDL plus concentrated loading, right? So usually is how much? So 10 kN per meter, 10 kN per meter plus 100. Now what is 4 meter? What is the total load for 4 meter? 4 meter total load is how much? 10 into 4 plus 100 is equal to 140. Okay, now what does it mean? It means that you can see here the difference in the order of the shear curve between any two sections. Okay, see I have to find the shear. Is to shear difference I find, right? Is how much? This loading into this distance gives what? The area of the loading curve, right? Plus this concentrated load. Because you can see here, this what? This is a UDL, right? This is a UDL into 4 is what? Area under loading curve plus this concentrated load, right? This is equal to 140. This is all equal to 140, right? So from this concept only we have found this value. So this is the answer will be what? The D. The answer. Now let us look at the question number 44. The variation of bending moment in a portion of a beam carrying linearly varying load. Now what is linearly varying load? This is, see, let us look at the UDL. This is a beam and this is what is UDL. W kilonewton per meter, right? This point is A, this point is B, right? Now what is linearly varying load? Here through the length the load is constant, but in case of linearly varying load, here it will be 0 at the start and at the end or the middle or somewhere else will be maximum W kilonewton per meter. I am showing at the end. Now I told you that bending moment degree shear force loading, right? This is what degree. Why? Because here the loading here is W into x to the power 0 What is the shear force? This is loading. What is shear force? W into X. What is bending moment? W x square, right? You will find x square comes right, the R A x minus W x square. You will find the shear force R A minus W x, right? So here 0, 1 degree more, 1 degree more, right? This is what parabola. But here, what is the loading diagram? What is the loading diagram? Suppose at the length x, this is L, right? About this is WX. So what is WX? So WX by X equal to W by L. So Wx is equal to what? W into X by L. That means what? Loading is how much? Loading is expressed in the power of X, right? W into X by L, X to the power what? 1. That means what? Shear force will be how much? Obviously W, shear force will have a power of X square. And what is the bending moment? Bending moment, it will have the power of what? X cube. You can see also what is shear force here. Shear force, suppose at this location X will what? RA minus half into X into WX equal to what? RA minus half X. What is WX? WL by X equal to what? R W by L X square, right? It's the same, right? So that means what? The shear force is 1 degree higher than the loading, and the bending moment is 1 degree higher than the loading. That is cubic parabola. So answer will be what? Cubic. It's not parabolic. This is for UDL. This is for linearly varying load. So answer is C, 44. Right. So the next question is question number 45. The maximum bending moment due to a moving load on a fixed and a beam occurs. So they are seeing the maximum bending moment due to a moving load, okay, on a fixed ended beam. Okay. Suppose this is a fixed beam. AB, then L. So the load P is moving from A to B. Right. Now they are asking the location of the maximum bending moment. Suppose this is P. What is C? They had this been a simply supported beam, the maximum bending moment would have occurred just under the load. But this is not a simply supported beam, this is a fixed beam. So in case of fixed beam, the maximum bending moment won't occur just under the load. It will actually occur just at the support, apart from the point center. See at the center, C, suppose this is the point C, suppose this is the length A, this is length B, L is what? A plus B. Now, if C is at the center, that means C equal to L by 2, then at that time, at that location, the maximum bending moment will simultaneously occur at the center as well as at the support. But apart from that center point, the maximum bending moment will always occur just at the fixed end in case of a moving load on a fixed beam. Right? In case of simply supported beam, what will happen? It will always occur just under the load. Okay. Now we'll try to prove this writing some example. Suppose this first we find a fixed C. We'll find a fixed and bending moment diagram. Then we'll draw the free and bending moment diagram. Then we'll superimpose and find a final bending moment diagram. Through that final bending moment diagram, we'll find the location of maximum bending moment. Right. Now the fixed and formula MA is what? About P is what? 10 kilonewton. And A is equal to 2. B is equal to 4. What is A plus B? 6. 2 plus 4, right? Equal to L. Right. Now what is MA value? Minus P into P square into A by A plus B whole square. You have to remember this formula. This is our standard formula. MB is what? Minus P into A square into B by A plus B whole square, right? So what do we get? We get MA is equal to minus 10 into 4 square into 2 by 6 square. Solving this, you will get minus 8.8 MB minus 10 into 2 square into 4 by 6 square, you get minus 4.4. Right. If I draw the bending moment diagram, what do I get? I get this. A minus 8.8. Right? Fixed bending moment. Right. Now, what is free bending moment diagram? What do you mean by free bending moment diagram? Free bending moment diagram is that diagram where you consider this into your simply supported, not fixed, right? So, free bending moment diagram, right? P BMD calculation. What is the value of RA? RA is what? P into 4 by 6 into 10 into 4 by 6. Solving this, how much you get? 5 20 by 3, 6.6. Right. Then what is the moment? Free bending moment at C. What's RA into 2? Into A, right? And 2, so 6 into 2, 35. So what is the bending moment diagram now? The bending moment. Where is this class, right? A, and it's called what? B, BMD. Now what we have to do? We have to superimpose, right? Superimposing will get a final BMD. So for this is minus 8.8 is minus 4.4. What you see now, you can see here the C, this is what? It is 2, this 4. That means the C point is near to the point A, right? If C is near to the point A and A is what? The M value is more than M value, right? That means C will be near to what? I take 6. It can be more than 6 also, but it will be 6 almost. But C is not at the center. It is closer to the point A. Now, if I consider this to be 6, suppose, like if you can easily find by solving through the help of similar triangle, right? So I'm not solving here the side, assume that it is approximately value equal to 6. It is not equal to 6 exactly, but it will be almost 6 or more than 6. Okay. This is suppose 6. This value is suppose 6. This is suppose 6 minus 6. And this value is how much? Already 13.2. What is the final value? This is the final value, right? This is the final value. How much you get this value? This value how much? 13.2 minus 6.6 to 7.2. Plus you get, for superimposing, plus you get 7.2, but minus is how much? Minus 8.8. That means what? The fixed and moment is more than the what? Superimposing bending moment, right? That means what? The maximum bending moment is not occurring just under the rule. This at the support only, right? At the support only. Now, if I take the load at the center, you can see suppose the load is at the center. Suppose load at the center. So at the center, what is the fixed end diagram? M is what? Minus P L by 8. How do you get this? This is error formula. But putting the value of A equal to what? A equal to L by 2, B equal to L by 2. On the MA formula and MB formula, you get this one, right? How much? Minus 10 into 6 by 8. So, sorry, 3 by 8, right? So, minus 7.5. At minus 7.5. Minus 7.5. 7.5. Now, what is the free bending moment? Let's see. Over L by 4 and into 6 by 4. So this is how much? 15. Right? So this is what? Minus 7.5, right? 7.5. That means in case of the load is at the center, the maximum bending moment will occur simultaneously at the center as well as at the fixed end. But if the load is not at the center, then the maximum bending moment in case of fixed beam will always occur at the support. What will be the answer? Answer is at the right. A. A cantilever beam AB of length L carries a concentrated load W at the midspan C. If the free end B is supported on a rigid prop, then there is a point of contact flexure. Okay. If cantilever AB, the cantilever, this is cantilever AB, the AB of length L carries a concentrated load W at the midspan C. See, this is a cantilever. It carries a concentrated load P. This is L by 2. This is L by 2. Okay. If the free end B is supported on a rigid prop, then there is a point of contact flexure. Okay. Where is the point of contact flexure? That is you have to find. This is A, this is B, this is C. Between A and C, between A and C, between C and B, one between A and C. See, there will be only one point of contact flexure. Okay, there won't be two point of contact flexure. So this option is incorrect. One between A and C and other between C and B incorrect. Nowhere in the middle is also incorrect. The answer will be what? Between A and C or between C and B. So to know where the point of contact flexure will occur. See from the concept here. See the concept. What is point of contact flexure? What is point of contact flexure? Bending moment changes sign, right? Bending moment changes sign, right? That means at that point bending moment has to be 0, isn't it? Bending has to be 0 at that point. Changes sign means what? It becomes positive, negative, or negative, positive. So at that point the bending moment has to be what? 0. So tell me from this diagram, can the bending moment become 0 at this location, right? No, because there is a load, this will give a reaction, and if you multiply with the distance, you will get the moment. This is what? This will give anti-clockwise, so there is no zero bending moment. But at some location here, A and C, the bending moment can be 0 because this load P is acting downward. So here anti-clockwise, here clockwise. This will nullify. Somewhere here I will get a 0 bending moment. So here I will get a point of contact flexure. The answer is what? Between A and C. Right? Between A and C. Question is a prismatic beam fixed at both ends. Okay. Prismatic beam fixed at both ends, carrying a uniformly distributed load. Okay. The ratio bending moment and the support to the bending moment at the midspan. That is the asking. So if you draw the bending moment diagram, what will the value? You have to remember this is minus PL square by 12. This is PL square by 12. Okay. All is a minus. This is minus. And this is how much? This is how much? This is W. This is W L square by 8 minus this W L square by 12. This is W. This is W. Okay. So how much? 24. 3 minus 2, 1. 3 minus 2, 1. Right. W L square by 24. Right. So here I'll have W L square 24. Here W L square 12. So they're asking at the support to the midspan. That means W L square by 12 divided by W L square by 24 is equal to 2. It has to be 2. What's the option? 47D is the correct answer. Yes, 47D. 2 is the correct answer. See, you have to remember here, like this is for UDL. Now for fixed, for simply point load, what is the value? This is how much? B. This MAB equal to minus PL by 8. MBA is equal to how much? Plus PL by 8. You have to remember this. It's fixed values. And for this is at the midspan, right? And if it is not located at a mid-span somewhere else, then also you have to remember the standard values. It is given in the book or in the handbook. Please see that you have to always remember those values, right? Okay, now the relationship between the radius of curvature is a very simple. Sigma by y equal to m by I equal to e by r, right? This is a simple bending formula. So what will happen? M by I equal to e by r. So how much we get? M equal to ei by r. This is the correct answer. 48b. 48b is the correct answer. Okay. Right. Now let us look at the question 49. A beam of overall length L with equal overhangs on both sides carries a uniformly distributed load over the entire length. To have numerically equal bending moment at the center of the beam and the supports, the distance between the supports should be. So this is a UDL, simply supported beam, carries this overhang. Okay, overhang. So this is A point, this is B point, and this is C point. And suppose this overhang length has got A, this is also A. Total length is suppose L, and suppose this length is C. So what are they asking? To have numerically equal bending moment at the center of the beam and supports. That means at this center, that means M A is equal to MC. If we are to get this value, if we are to get the value of M equal to MC or M equal to MC, then what should be the distance C? Right? Distance C is the distance between the supports A and B, right? This you have to find for this M equal to MC. So how to calculate? First, the reactions. Reactions RA. This is how much? W kN per meter. The RA equal to RB. How much? W into P plus 2A by, right? This is the value of RA. That is now, what is the value of MC? Moment at C. RA into C by 2 minus W into A plus C by 2 into A plus C by 2 by 2. So solving this, you get MC equal to W8 by A square minus 4A square. You get this value, right? Now, what is MA? MA is how much? Obviously, W A square by 2. So this equal to what? How much? W by 8 C square minus 4A square. And if you solve this value, you find A equal to C by 2 root 2. Right? A equal to C by 2 root 2. Now, what is C? C is how much? L minus 2A into L minus 2C by 2 root 2. Solving this, you get C is equal to 0.586 L. So this is the answer. Okay, this is the answer. Now, question number 50. Prismatic beam of length L. The prismatic beam of length fixed at both ends. Okay, fixed at both ends. Carries a uniformly distributed load. 50, right? Carries a uniformly distributed load. But this is the point of contact formula either end. Okay. So now what is the bending moment diagram? This is the bending moment diagram, right? So you have to find this value, this x, right? You have to find this x. So this is RA, RB. So what is RA? R is what? W, L by 2. This is L, and this is W kilonewton per meter, right? R equal to mass WL by 2, right? Now what is the fixed time value? This is how much? This is, I told you have to remember this minus PL by 8, right? This minus PL by, this is the bending moment diagram, minus PL by 8. So you have to find this here, the bending moment is 0, right? So let me write the equation of bending moment 0. RA, suppose this point is C. So bending moment at C is equal to 0. So RA into X, right? Minus, so sorry, this is WL square by 12, okay? WL square by 12. This is 12. Okay, this is 12. Minus WL square by 12 minus for this UDL W x square by 2 is equal to 0. So I think if you solve it, WL by 2x minus WL square by 12 minus WX square by 2 to 0. If you solve it, you get this answer. X equal to 0.211 L. You solve this, you get this answer. Okay. Right. Now let us solve the question number 41. The simply supported beam of length L carries a load varying uniformly from 0 at left hand to the maximum at the right hand. The maximum bending moment occurs at the distance of. So here, right, this is the A point, this is B point. Here W kilonewton per meter. So what is the maximum bending moment? So to find the maximum moment, we have to write the equation of bending moment. So here, let me write the value. RA is how much? R is WL by, see, you have to remember this WL by 6, RB is how much? WL by 3. You have to remember the standard value. You can find this value by equating the moment at B equal to 0 or equating the moment at A equal to 0. Then you can find, but I have written directly, okay? So suppose at the point C, the bending moment is maximum, right? At the point C, the bending moment is maximum. So here WX is how much? WX by L by similar triangle, right? This is L. This length is how much? L. So bending moment at C is how much? RA into X minus half X into WX into X by 3 is equal to WL by 6X minus half X WX by L X by 3 to WL by 6X minus WX cubed by 6L. So if you want to get the maximum bending moment, we have to differentiate. So dm by dc how much? Is equal to 0. So WL by 6 minus 3 WX square by 6L is equal to 0. Solving this, you will find X equal to L by root over 3. So answer will be this X equal to L by root over 3. So 1 by L by root over 3 from the left hand. Right? This is the answer. This way you can find. If a cantilever beam carries an uniform distributed load over its entire length, then the shape of the shear force diagram and a bending diagram respectively are. So there is a cantilever carrying a uniformly distributed load over its entire length, the shape of the shear force diagram and the bending diagram. So this is what UDL. UDL means what? The shear force will be what? 1 degree higher than the bending moment. Loading. Loading is what? Wx equal 0. So shear force Wx bending moment, Wx squared. This is what? Linear, and this is what? Parabolic or quadratic. So answer is what? First is shear force diagram. Shear force diagram is obviously triangular, right? And this is quadrilateral. This is the correct answer. 52B. 52B is the correct answer, right? So next question is, a portion of the beam between two sections is said to be in pure bending when there is constant bending moment, zero shear force, constant shear force, constant bending moment, and okay. Pure bending means what? Where there is no shear force, and there is no shear force. Okay, in pure bending there cannot be any shear force. Okay, so we'll find zero shear force. There is zero shear force. So answer is what? constant bending moment and zero shape. This is the correct answer. 53A. 53A is the correct answer, right? Now let us look at the question number 54. The ratio of width to depth of the strongest beam that can be cut out of a cylinder log of wood. Okay. Suppose this is cylinder, okay? The cylinder, okay? This has got a diameter D. Okay. Now, what you have to do is that you have to cut a rectangle from this circle. Okay, suppose let me draw a circle here again. And this circle. You have to draw a rectangle such that this rectangle has got a maximum Z. Z, right? Z is what? Sectional modulus, right? Okay, that is strongest beam means what? That you have to get a maximum Z. So suppose this is B and this is D. That means what is Z is how much? B D square by 6. That means you have to make P and D in such a way that this value will get maximum. Okay. So what is, let me say, this is diameter, right? This is the diameter. So we can write according to Pythagoras formula, B square plus D square equal to D square. Okay. Now what is Z? Z is what? B D square by 6. So to get maximum, like strongest beam, so this Z has the maximum. So dz by like db, when difference with respect to b, we get 0 or because this Z has the maximum. So db, right? B. Now what is d square? D square is how much? D square is b square minus b square, right? So b db b d square minus b cube is equal to 0. So b square minus 3 b square is equal to 0. So b is equal to d by root over 3, right? So if b equal to d by root over 3, from this equation, d by root 3 square plus d square equal to d square. So d square is how much? D square minus d square by 3 equal to 2d square. D square by 3, sorry. So d is equal to how much? Root over 2 by 3 d. So what do you have to find? Ratio of how much? What is the question? Ratio of depth with to depth. That means you have to find d by d. So d by d is how much? D is how much? D by root over 3 divided by what is d? Root 2 by root 3 d. So ultimately what do you get? You get 1 by root over 2. 1 by root over 2 is the answer. 54B. Okay. Right. Because you have to find a Z. If you get a maximum Z, then it becomes a maximum, strongest B. Right. That is what we have to find. Okay. Now, next question is, the next question is, of the several prismatic beams of equal length, the strongest in flexure is the one having maximum sectional modulus. Remember this, sectional modulus. Okay. Of the two prismatic beams of same material length is straight. One is circular, the other is square in cross section. Ratio weights of circular and square beam is, okay. Same material length and flexural strength. Okay, one is circular, the other is square. Ratio weight of circular and square beams. Okay, that means Z is same. Z is same because same flexural strength is given, right? But what will happen? The area is cannot same, right? The area is different, isn't it? Area is different, right? So area, first of all, the same length and same circle. So what is the area? Area of circle is what? Pi d square by 4. Area of square is what? Let me write b square. B square, right? That means it's pi. Okay, now j of circle is how much? Pi, pi d cube by 32, right? Now j of square is what? Pi d square by 6, right? Pi b square by 6. Pi b cube by 6. I'm sorry. Pi b cube by 6. So this pi b cube by 32. Now, let me draw. Now, let me draw. Let me draw question 56. We have two prismatic beams of same material length and material strength. One is circular, the other is square. There is a weight of circular and square beams. Okay. Now, see here. See, same flexural strength means what? The Z is same. So Z of circle is Z of square. So pi b cube by 32 is equal to b cube by 6. Right. Now we have to find a weight difference. Now weight difference you will find when you notice the area of the both section, one circle, one square, right? Because the length is same, right? If you multiply the area into length, you get different volume. So if the circular has more volume, then it will be more costly, right? It will have more what weight, because what, same material given. That means what, the thickness, the density is same, right? So to find the area now. So here what we get, pi d cube by 30 d cube by 6. That means what we can find here, d is equal to 32 by 6 pi to the power 1 by 3 b, right? 32 by 6 pi to the power 1 by 3 b, right? This is what you get, right? This is what you get. Now what is the area? Area pi d square by 4. The area is what, b square. Area is what, b square. Now you can see here the value of d is expressed in terms of here. Okay. Now if I find this value and find this value, let me find pi by 4. What is d square? 32 d2 by 6 pi to the power 1 by 3 square, right? Into b square. Okay. How much? Pi by 4 I am writing here. 32 by 6 pi 2 by 3 into b square. Now find this value. If find this value, because right, this is what? This is the area of the circle, right? This part is what? The area of the circle. Now you find this value. If this value is right more than 1, if this value is more than 1, what does it mean? The weight of the circle will be more than square. Now if this value is less than 1, then the weight of the circular section is less than the weight of the square section, because what, length is same and what, material is same. Density, material is same means what, density same, length same means what, same length. That means the volume, you multiply the area to volume, then the more is the area, more is the weight, right? Because the material is same. Now what is this value? So pi by 4, 32 by 6 by 2 by 3. So I think this value, right? This value is, right? This value is more than 1. This value is more than 1. That means what? Circle will have more weight. So, and more weight. And what do you do? And what I have to do? I have to do a ratio, right? Ratio of weight of circle and squaring. So I divide this by b square, right? Now this is the value. This value is the answer. So let me write pi by 4 into 32 by 6 pi divided 2 by 3. So I think this value is very so much 1.118. This value is 1.118. 1.118. 1.118. So this is the answer. 1.118. Okay. Wait. Next question is, a beam of triangular cross section is placed with its base horizontal. The maximum shear stress intensity at the intersection will be. So here is a triangular cross section. Okay. Now, if I look at the shear stress distribution of the triangular section, this is the CG. Okay, this is the neutral axis. Here, this is the maximum. Maximum is at this location. This is at the mid section. Okay, mid, h by 2, h by 2. That means this location is what? Higher than this neutral axis, right? So answer will be what? Above the neutral axis. This is the neutral axis. This is CG also. Here, you won't get the maximum shear stress. You are getting at this location, this C location, right? C. Above the neutral axis, right? Next question, 64. A beam of I section 600 mm deep and 200 mm wide has flange 25 mm thick and wave 20 mm. If the shear stress in the wave at the junction of flange and wave is Q, then the shear stress in the flange at the junction is, okay. First, I have to draw the I section. Let me draw the I section first. I'll draw the shear stress diagram. First, let me write the value. This is 200, I think. And this is 600. This is much 25. And this is 20. This part is called the flange. And this part is called wave. This is the junction. Now I draw the shear stress distribution diagram. If I draw it, it will be something like clearly you can see maximum is at the center, right? At the neutral axis. And this is junction, okay? See, at the flange part of the junction, the shear stress is less than at the wave part of the junction. You see the wave part, what is happening? Suddenly the shear stress is increasing at the wave part, okay? But at the flange part, the shear stress is less, okay? Now, what is the shear stress formula? Q is what? SA Y by I B. S is what? Shear force. AY is what? Moment of area of the portion above the location where shear stress is calculated. Okay, calculated. What is I? Moment of inertia of the whole section. What is B? Width of the layer where shear stress is calculated, right? So here you can see here you have to find the shear. See, in a question given, with the shear stress in the wave, okay, this is the wave, right? At a junction is Q. That means here this says what Q at this location in the wave is Q. Obviously, from the diagram you can see that the shear stress in the flange on the junction is less than Q. This is the value, right? Right? If this is Q, this is the value. Obviously, this value is less than Q. So answer will be either 0.5 or 0.1 Q. Which one is the correct answer? Now you can see here, this S is constant, I is constant, area also constant, Y also constant, Y dash Y, because you have to find AY from this location only, right? This is the layer, right? This is a layer. This is a layer. Above this layer, you have to find the AY dash value. About this CG, neutral axis, right? That means what is changing? Only B. How? B for the wave is how much? 20. See, B for the wave is what? 20. But when we calculate the shear stress for the flange part at the junction, the B becomes what? This whole B, right? This becomes 200. But 200 is what? 20 times more than what? Sorry, 10 times more than this 20, right? That means the shear stress will become what? 10 times less than the shear stress on the wave of the junction. So answer will be what? 0.1 U. Right? This is the answer. Because B becomes what? 200 in case of flange. And here B is what? 20 in case of wave. Right. Next question is, a beam of uniform strength has an average cross section same. Remember bending stress. When you say about uniform strength, remember always you have to have uniform. Every cross section you have to have bending stress. Next question is, shear center in the channel section is shown figure. What is shear center? Shear center is that location through which only bending will exist. Only bending. No twisting. If no twisting, no torsion, right? So this is the beam, right? So if you apply load, vertical load, if you apply this B point, there will be only bending, but no what? No twisting. If you apply load from any other point, there will be twisting moment also. So that particular point is called shear center. So in this channel section, the shear center is what? At the location B. For different section, I section, angle section, triangle section, there will be different triangle section, there will be different shear center location. But for the channel section, the shear center location is at B. So 66 answer is B, right? At B, B. Okay. Next question is, for no torsion, the plane of bending. Same question, for no torsion, the plane of bending must pass through the shear center of the section. Okay? For no torsion, only bending is there. Next question is, two beams, one of circular cross section and the other of square cross section, have the same equal area of cross section. If subjected to bending, I already solved the question in 56 number. You can see one of the two prismatic beams of same material length and flexural and one is circular, the other is square. The ratio of weights of circular and square beam is, obviously the ratio is 1:118. That means circular cross section has got more weight than the square beam. If the length is same, material is same, that means what? If the weight is more, that means what? You have to use more dimension, right? That the cost will be more, isn't it? In case of circular, the cost will be more. So square becomes what? More economical. The answer is what? 68B. Square is what? More economical. 69. Okay, before. Okay, 69. The portion which should be removed from top and bottom of a circular section of diameter d in order to obtain the maximum section modulus. Here there is a circular section. Okay. Now this is diameter. Now the portion you have to remove from top and bottom so that you can get the maximum sectional modulus. Now what is sectional modulus? Z from the circular pi d cubed by 32. Now this value is not maximum for this section. If you remove some portion from top and bottom, you will get a maximum sectional modulus. Earlier we solved a question. Suppose we solved a question where one rectangular cross section was taken from this circular cross section. Okay. And we are asked to find the maximum sectional modulus of the rectangular section. Here in the earlier question, we found the sectional modulus of the rectangular section, right? The strongest rectangular section. Here we don't need to make any rectangular section. We have to make this circular section stronger, but this value is not a stronger one. So how to make this to be more stronger one, right? The question is, see, the portion should be removed from the top and bottom of the circular cross section of diameter d in order to obtain the maximum sectional modulus. Okay, of this, right? If we want to have the maximum sectional modulus, what value we should remove? Okay, so if you remove 0.011d and 0.011d from top and bottom, you will get the maximum sectional modulus of this particular section, right? Answer is C. You have to remember this. This is C. Okay. Next question is a beam of overall length L rests on two simple supports. Suppose these are two beams. Okay. Equal overhang. A overall length L. A, B, C, B. Two equal loads X at the free end. So two equal loads acting P, P. If the deflection at the center of the beam is same as at the other end. So suppose this is the center of the beam E. Let me draw a deflection diagram also. So what will be deflection diagram? This is a deflection diagram, right? This is delta C, delta. This is slope E. This is also slope E. Sorry, slope A. I'm sorry, slope A. Okay. So you are asked to find if this delta is same, then length of the overhang. That means this A value is how much? What is this A value? What is the length of this overhang, right? So to find this, first what we do, we have to simplify this structure. Okay, let us simplify this now like this. This A point, B point. Now what is the moment? P into A, right? P into A is the moment. What is the moment here again? Moment is what? P into B, right? For this vertical load P, what is the moment at A? P into A only. This is the point E. Now because of this moment, there will be deflection and slope at the A and B. This slope value is always, remember, M. This is phase value so much? L minus 2A. L minus 2A. Okay. M length AB by 2EI equal to M L minus 2A by 2EI. Okay. And the deflection at E, because of this moment, okay, deflection is how much? Deflection delta E is how much? M L minus 2A whole square by 8EI. Remember this. This is standard value. If two moments are acting on a simply supported beam, equal moment, and the moment deflection at the center is what? ML square by 8EI, and the slope is ML by 2EA. Okay. Now this is what? Now this value is equal to how much? This delta is how much? Equal to delta C. Now what is delta C? Delta C we can calculate by two methods. One, this is, suppose this we consider this to be fixed. If this is considered to be fixed, what is the deflection? P A cube by 3EI 3EI plus there is slope here, right? Because of this slope there will be deflection at this end. So this is what? Theta A into A. That means PAQ by 3EI. What is theta A? Theta A is this value. M L minus 2A by 2EI into A. What is the value of M? EI plus M is what? PA L minus 2A by 2EI into A. This is what? Deflection at C. This is what? Deflection at C. T is equal to this deflection at E. And through that you will find that length A is how much? 0.152 L. You solve it, you will find the value. Remember, you have to simplify this and take moment here, because obviously moment will be applied because of this cantilever portion. So here you can solve it, right?